The talk today is titled Celestial Diamonds, and then hopefully soon I'll explain what we're calling a celestial diamond. And it's work that should be written up and out in the archive very soon with Andrea Poom and Emilio Trevisani. So thank you guys for having me and letting me talk. I'm going to minus you guys so I can see what I'm doing. Great. Okay, so the goal of today's talk is going to be to try to connect this very interesting null state story that we're seeing in Banerjee and Ghosh and collaborators' work recently, conformally self-dressing that we've seen with lots of people at the bottom here with Andy's crew, and some recent celestial effective field theory stories that have been emerging. And we're going to do this, I guess, with a relatively simple starting point, which is to just be very systematic about the global primary descendants in celestial CFT. And for me, I'm actually talking about just global SL2C right now. So even though at first, so what we're basically going to be trying to do is start from just writing down all of the primary descendants that can appear just from the representation theory of SL2C. And we're going to be doing it from the point of view of showing what's happening in the bulk so that I guess it becomes clearer when you see these states that Andy's talking about with these finite dimensional representations, what they mean with respect to wave functions in the bulk, which was related to like what Joffrey was asking. So let's just start with some nice representation theory. So say you give me a primary state with the holomorphic and anti-holomorphic weights H and H bar, then I would I would call it a primary because it's annihilated by L1 and L1 bar, and I form descendants by acting with L-1. And just from the SL2C algebra, you see that you get a primary descendant at level K if H takes on this value. So right now, K is some integer that's positive, and basically if H is 1 minus K over 2, then I get this primary descendant. Do the same thing for the anti-holomorphic guy, and I would similarly get a primary descendant when H bar takes on these special, I guess, half integer values. Good. So now if I had only one or the other, then we're basically done. You have a null state in the, like that would correspond to basically having not both conditions satisfied. So you can imagine if delta were not special, then that could be the case, but you need to have basically the spin be a bit weird. Now, the fun thing about it is, especially for the context of celestial CFT, because we often have these fixed integer spins, basically once you go to certain values of delta, you're going to find that both H and H bar satisfy the appropriate conditions to have primary descendants. And once you have both a holomorphic and anti-holomorphic primary descendant, you actually get a third guy, which closes up the structure that I'll refer to as a diamond in various parts of the talk. And it's basically just a diamond of nested submodules for these SL2C representations. So right now I've only shown basically the primary descendants that descend, but there are K-bar steps here, K steps here of other states in that module. Good. Okay. So let's make a couple of comments before I keep going further. Every time I have a primed quantity, I'm going to be referring to the child, so the primary descendant of the primary that had weights corresponding to H and H bar. And those primary descendants are going to be related by a Wall refraction of H. Then also at some points, I'll go back and forth between writing everything in terms of the state with a definite weight and using the state operator correspondence and sometimes mixing H's and deltas and J's. So when I do that, then basically everything I'm talking about with regards to SL2C descendants just becomes W derivatives or W bar derivatives hitting my original primary. So one other thing to keep in mind, which is something that I'll return to later, is that primary descendants need not be null. And so part of the unpacking that we're doing here, even though we're starting with something relatively simple, is to just keep in mind what things hold because of I guess the symmetries that you still have in celestial CFT and what things might come from, I guess, the like radial quantization versus the intrinsic Hilbert space that we inherit from the 4D bulk in celestial CFT. So we want to basically redo these things, and we're trying to perform a classification of these null states in the same manner that my co-author Emilio and Yaupanadonis and Masahito were doing for generic D CFTs, but normal CFTs, so not with not celestial CFTs. And they're like that classification procedure lands on some nice general statements you can make about the conformal block decomposition. So now I'm going to talk about the different categories that these primary descendants fall into. So the first definition is a type 1 primary descendant, and that's going to have the child primary descendant having a 2D spin larger in absolute value than the guy it descended from. These type 1a and type 1b take the following form in terms of the state operator correspondence, and they appear at these special negative integer values of delta. And for all, there's this infinite tower that Andy was referring to. So we're going to talk about basically these different null states that are appearing, what types they fall into under this classification, which is trying to be a bit systematic. So this class naturally divides into two subtypes, basically depending on the level. And so because some of these things also appeared in early Banerjee works, we adapted the higher D classification from Emilio Petidonis et al.'s paper to something that reflects more naturally, I guess, the structure of these submodules. So you could choose to say that 1A is only the holomorphic guy and 1B is the anti-holomorphic guy, but that kind of misses, I guess, the reflection under one helicity to the other. So right now, it's better to keep track of it in terms of the different levels. So now let's move to type 2. The type 2 primary descendant will have the spin of the child being less than that of the parent. And so for these guys, again, there is a range of delta for which this occurs, but it's now a finite range. And we're going to see that these guys are the ones that are intimately connected with the soft theorems with a corresponding asymptotic symmetry interpretation. So for fixed J, which is what you normally think of in celestial CFTs, we'll see later, because you have either a gluon field or a graviton field, et cetera, in the bulk, this would imply a finite range of special values of delta. Now for type 3, you have much more restrictive. So type 3 is almost, in some sense, like the border between type 1 and type 2. You have basically just the 2D spin gets flipped. And so you go from primary with spin plus S, if S is the 4D spin, to negative that. So now that only occurs at one value of delta, and this is precisely going to be the most subleading soft theorems. So the structure that I'm talking about now, while it is still somehow starting from something basic, is going to kind of illustrate where each of the different soft theorems are appearing, where the different finite dimensional reps that Andy is talking about that are interesting from the point of view of finding all orders, like of the OP coefficients for these oh, sorry, I don't hear the question. So basically, like the point is to go through, use this classification to kind of identify where all these interesting structures were appearing in our amplitudes. So before going to the celestial CFT story, I want to just draw, I guess, the plots that are appearing here. So type 1, type 2, and type 3 have the parent primaries being in different ranges of delta and J. The plots that I've drawn right now would be assuming that J is integer, which is where you would then naturally have the dots basically aligned with being centered at delta equals 1, J equals 0. And when you have that, you have basically this full gray region of certain negative values of delta for which you would expect both a holomorphic and anti-holomorphic primary descendant. And then similarly for type 2, there is this range. So at a given value of J, basically, I have this semi-infinite set of where I can have different null states. And you can see that the boundary of those two regions is type 3. So when Andy was talking about an infinite series of these symmetries, he was actually talking about an overlap here between the three different guys. So the ones that he's starting with are going to be type 2. Those become then type 3, which are the most subleading soft theorems. And then you have type 1. So basically what I want to point out is even though maybe there's some sense in which like it's good to be keeping track of the distinction here, because once you go to this wave function approach, you'll see that for the type 1 guys, these number of derivatives that land you on primary descendants actually just trivially give you 0, versus the notion of being a null state versus being a primary descendant is a bit murkier in celestial CFTs, so one needs to be careful so they are not quite on the same footing. Good. Okay.
Sabrina, could
Yes.
you just say, wait, the red dot, which are the red dot is, the red dot at the corner of the L is the state you're starting with?
So the red dot at the, like, in any case, it's the topmost guy that you're starting with because the dimensions get added whenever you take a derivative in W or W bar. So the descendants are going to always be down. So in this case, the top guy here is this primary descendant and is the primary, and its primary descendants are the type 1A, type 1B. And for any different, so this diagram is supposed to show that you could start at different values of delta and J and still have these primary descendants. So the colors match like basically the other structures that you would get. So we'd start with the orange dot, and its primary descendant would be at this orange dot versus at that orange dot. So, and then the same, now here, the fun thing is that they, there's chances for them to overlap. So the earlier work of Banerjee actually is kind of probing this in a fun way also. And basically we're trying to connect that to the story of like, basically by looking at all primary descendants, how his story falls into the same place as your story, et cetera. So, good, okay. So now what I want to talk about is this diamond structure. So because of the fact that our spins are integer, you end up, for these special values of delta, often satisfying both the H and the H bar, matching the conditions you need to have a primary descendant. And so then you have this diamond structure up here. So within the classification that I just gave, if I have some state here at the top of this diamond, then I have a type 1a descendant and a type 1b descendant, where 1a versus 1b is basically like which one is larger. If k bar is smaller than k, then I would call that one the type 1a and type 1b. It's a little bit arbitrary, but at least the asymmetry of it is actually relevant from the point of view of whether or not the soft theorems are chiral. So like the leading soft theorem having this redundancy between the two velocities is related to the fact that it's not skewed. So then the bottom of this diamond is going to be a type 2 descendant, type 2 primary descendant of these type 1a and b primary descendants respectively. So you have these nested submodules, and normally in a couple slides I'm going to talk about whether or not you would actually end up quotienting by these. In celestial CFT you don't. Good, okay. So before I move on to celestial CFT specific things, there's another thing that I can say just that's true for any CFT, which is that if I have this diamond structure, so I have these 1a and 1b descending from the same state, then I actually have that the 1a and 1b are the shadow transforms of each other. So, and one other thing to point out is, I guess, relevant to this, is that basically there's another transform which you can imagine just basically inverting the descendants that take you from this top primary down. So there's another integral transform you can create that takes you from either of the left or right corners back up to the top at the price of missing the kernel when you descend back down. In a couple, hopefully by the end of the talk, we can maybe make more interesting interpretations of when you would do that or not. But right now, the interesting statement here is that basically when you have this diamond structure, you have the left and right quarters weighted by shadow. And why that's important for our story in celestial CFTs will be that we see that sometimes, like the stress tensor, for instance, is a shadow of a delta equals 0 mode. And you're going to be wondering, like, why is it that I need to like do the shadow or not? Well, all of the soft theorems where these shadows are appearing are basically in this ascendancy structure where if you add a state at the top of the diamond, then you get the shadow and the non-shadow modes for free. And so somehow the point of this talk is to eventually motivate that by looking for this parent structure, you end up, I guess, seeing the states that are going to come in for conformally soft dressings, et cetera. So that's the picture to keep in mind, is we're doing this thing with just this representation theory of SL2C, and we're hoping to learn something about different conformally soft dressings and other interesting stuff that's happening now in the field. So, okay, so type 3.
I think Lee has a question.
Yes. Hi, Lee.
Lee,
I think
You're muted.
All of
You're
this,
muted, Lee.
Oh, you're muted at first, now you're back.
yes, all of this is very beautiful representation theory.
Yes.
How much can you get back to functions on a two-sphere in a manifold near Scri plus or on Scri plus and so forth? That is,
Yeah.
you've got a completely algebraic representation theoretic picture. Do you need to go back to space?
So I would. So the reason why I want to go back, and so if anything, the part of me that wants to go back is because the last paper with Andrea, we were really interested in looking at interesting bulk solutions like, say, the Eichelberg-Sexel geometry that formally are also conformal primary wave functions. But and then there's also this question that Joffrey was raising about like what values in 1 over R do these guys fall off at? So essentially right now I've done something just completely abstractly, and I guess it's also like a simple group to have started with. But once you then do the same thing for these profiles that have definite conformal weights in the bulk, you can see that these operators correspond to states with different fall-offs in 1 over R for like the metric field, for instance. And so then you can like start attaching meaning to like, do I want to include this with my boundary conditions, et cetera. And that's part of the point. But the other part of the point is that everything that Andy's doing at the level of looking at OPEs and amplitudes, a lot of those statements can be made just from the wave functions. And so then, you know, you're creating these scattering states by taking an inner product of your operator with this profile. And so if a relation holds at the level of that profile, then it holds in the amplitude too. So
that's what I'm wondering. Do you have a theory of an S matrix scattering of gravitational degrees of freedom without having to make reference to classical geometry?
I mean, I'm assuming that if anything, okay, so I want to then highlight the work of Banerjee and all, and I think I actually like this a lot, and it's something, the more you read it, the more you understand that like it's actually an interesting approach. So the question that this also gets at is kind of what happens at 2D CFTs versus higher dimensional celestial CFTs. And I think the answer, if you like from our interpretation of this, then looking back at the earlier papers by Banerjee, is that somehow the structure of these top states in the diamond that you'd add for addressing persists to higher dimensions. So what, I guess that's my side of why I think it's interesting to look at this, but also from answering your question, what Banerjee's point of view is that he could identify these certain spectra as appearing just from the representation theory of the free, like, so you start from the free theory, like just described in terms of like creation annihilation operators with points on the, I guess, like the momentum directions, and then also an energy coordinate. And in some sense, it's a kind of disconnected from any bulk interpretation at the moment. And so then he goes through like a little group or light ray analysis of those guys, and he can identify from just the spin of the field, I guess, what conformal dimension the soft charge operator should be. And then he tries to basically create something very similar to what I'm calling the celestial diamond by looking for the class of primary descendants. And when you do that, you get this effective lower dimensional field equations for these guys. So you can definitely try to take this approach. And if anything, I think that was what Banerjee was starting to do. But what I'm going back with it with this, I guess, bulk interpretation is to connect what he was doing to this asymptotic symmetry story. Because in some sense, he's saying that you have these conformal primaries, and because it's a primary, you can somehow consistently set it to 0. And it's a very powerful statement, but it doesn't necessarily connect as easily with what's going on in the bulk as far as what the asymptotic symmetry statements are. So if anything, I would say that like the part that I'm adding to the story is because I also know what's going on in the bulk now. But you can this definitely has a lot of power. The question is sometimes like can we make this statement? Yes, but should we make this statement? Like I say that you can do it at the level of the wave function as opposed to at the level of checking soft theorems, for instance. So. So if I can just even advertise with some of the earlier papers by Banerjee, that's great because they're actually really cool. So yeah. Great. Okay, so now I'm going to specify to celestial CFTs. And I'm going to be taking this wave function based approach that I guess I've advocated before. And so I guess the 3 reasons why it's interesting and not like, I guess, trivial in some sense, you could say, oh, you're just looking at like bulk to boundary properties, basically. Is that you're going to see that which relations you're using hold at the level of the kinematics versus actually rely on conformally soft dynamics or something, I guess, not just coming from the kinematics. The second thing is that you now have this bulk interpretation of these states you're creating by like Taylor series essentially expanding on the celestial CFT. And so with that, you then have this notion of like, what are the boundary conditions allowing these modes, et cetera. And the third thing is that because I can do everything at the point of view of the wave functions, if it holds at the level of the wave function, it will hold at the level of the celestial amplitudes. So in some sense, I have I'm going to be creating these objects that are like the nicely transforming elements, building blocks that I can put together and build up any wave function that I want. And it's more of like the poor man's trick to doing representation theory in the same way that one would take symmetric polynomials and find representations of the symmetric group. So, okay, so let's start by revisiting the definition of a conformal primary wave function. And by revisiting it, I mean taking a little step back. And so this also will connect to one statement that Andy made in his talk. So for me, the definition of a radiative conformal primary wave function is that it's a wave function on R1, 3. So right now I'm in 3 + 1. which satisfies the linearized equations of motion and then transforms under SL2C in the following covariant way. So I do a Lorentz transformation in the bulk, I do a Mobius transformation on the celestial sphere, and I get back definite weights, and I have some representation here of the field. And the important thing is that the 4D spin, or helicity, I guess in the massless case, is equal to the spin on the celestial sphere. Now, the fun thing about that is we're going to show in a couple slides that actually amounts to basically doing a gauge fixing. And once you relax, then in the next slide, I'm going to define a generalized conformal primary to basically relax those extra conditions you're imposing. So if you, imposing the EOM is enough to basically pick a gauge. So being conformal primary, being S equals J, and solving the equations of motion is a gauge fixing. And once we go to generalized conformal primaries, where we don't try to connect the 4D and the 2D spins, you end up getting a lot more possibilities. So if we want to build up all those different possibilities, and part of the reason why you might be interested in it is, say you want to look at interesting geometries like the Eichelberg, Sexel, Ultra Boost, or like the spinning analog of that, there's a lot of wave functions you can construct which transform like this guy and not like the guy before where S equals J. So go about doing that. So this is just a little bit of, I guess, tricks of the trade for getting these representations. And I do want to point out that somehow I'm an advocate for keeping the reference direction and the space-time, I guess, celestial sphere coordinate that you'd get if you went to Bondi coordinates separate, just so that you have this ability to play around with taking derivatives in W versus leaving the X profile, the Z profile fixed, because sometimes when you do the Mellon transform, you kind of, I guess, lose sight of that independent, that naive independence there. So right now, I'm just going to find this reference direction to capture this celestial S2 dependence. And then under SL2C, because I've defined this 4 vector to really only depend on the reference direction, if I do a Mobius transformation, it's not going to exactly be Lorentz in the bulk. I get some Jacobian here. So now what I want to say is if I wanted to build an arbitrary generalized primary wave function, I have a certain finite number of building blocks. So my start with a generalized scalar. So I know that it has to basically have the same overall factor of CW plus D absolute value that comes from this negative Q dot X, and then I multiply it by an arbitrary function of X squared. I then want to build up a tetrad which also has definite SL2C weights and a spin frame if I want to go to the half integer spin case, where I can then just multiply my scalar with these guys and construct whatever wave function I'd like. So a natural way to do this, and this is somewhat similar to what you would do for the massive case, is to start building a null tetrad. And when you do that, you have basically the null reference direction, the polarizations at your disposal. And it's nice to use X mu also as one of your, I guess, 4 sets of vectors that span the tangent space at most points. So I can build up these tetrad elements that I've written down here, and these all have dimension 0 and spin 0 for L and N, and plus or minus 1 for M and M bar. And another nice thing about these guys is that if you do the naive gauge transformation would correspond to shifting epsilon proportional to Q, and these guys are constructed to be invariant under that, which is fun. So it obeys all the standard orthonormality conditions for this null tetrad, and further can decompose into the spin frame. And the spin frame is just written here. So up to a factor of Q dot X, which basically is in Taylor's paper where they talk about supersymmetry, you see these like delta plus a half appearing in different places. If you push that into the definition of the spinner, then you kind of can see like that the scalar wave function is determining the dimension, and then these tetrad or spinner frame elements are giving you the spin part. So now I can build up whatever primary I want, and this was also a little featured in Andrea's talk at the conference at Princeton, by taking just tensor products of these guys with my scalar and some arbitrary function of X squared. So now if I want to go about and try to construct wave functions with J less than S that still, for instance, maybe satisfied the equations of motion and the gauge fixing conditions of the radiative guys, you'll actually see that there are non-trivial solutions. So I'm going to look at the spin 1 case as an example. So the bulk spin 1 is a gauge field, and then look at the J equals +1. The -1 case is just the complex conjugate here, basically, and the J equals 0 case. So essentially, what I had mentioned before was that I somehow have there's a gauge fixing implicit in demanding that J equals S. I only have one tetrad element free here, versus for J equals 0, I have two free functions that I can try to solve for. So I can just be able to do this for all different values of spin. So that's where it's nice to keep that in mind. If I look at radial gauge, it's automatically satisfied. If I look at harmonic gauge, also automatically satisfied for the radiative guy. And if I look at then the equations of motion, I constrain F to basically land me on either the conformal primary wave function that's gauge equivalent to a Mellon transform or its shadow. And one thing to point out here is, so basically solving all of these together, any delta in the complex plane is allowed. The delta in the 1 plus I lambda principal series is a basis if I pick either the shadow or non-shadow. If I do the exact same thing for the second row here, I end up finding that only discrete spectrum satisfy this. So these are the going to be the guys with, so now J is less than S. So J is 0 here instead of it being a helicity 1 field. And what I have now is basically two solutions and only one value of delta. And what's fun is it's basically picking out for me the Goldstone and memory modes that these are going to be type 2 primary descendants of certain special radiative guys. Okay, so in a couple slides, we're going to see that this procedure is landing us on these type 2 primary descendants of radiative modes. And that picture is consistent with the fact that, okay, so the radiative guys satisfied all of these gauge conditions, even though I guess the gauge fixing would maybe more naturally be it's a conformal primary. If you take any W or W bar derivatives, it commutes with those functions of x squared or derivatives with respect to x. And so all of the gauge conditions will still be satisfied. And so you basically land on any primary descendants of the radiative guys, and there's only a finite number. So it's fun to also compare this with the route of Banerjee et al., which I was mentioning before, which is basically he's identifying the value of delta at which these type 2 primary descendants are occurring. And then he's working his way up to see where they could have descended from, and then trying to talk about whether he can quotient things out. So that's like basically it's a space-time way to land at what he's doing in a way that's very abstract and not looking at what's happening in the bulk. So before proceeding, it's worth pointing out, like we have all this evidence about primary descendants. When are they actually null? So if I just look at the way that these wave functions are transforming in the bulk, I have a connection between what's happening in the x coordinate and what's happening with respect to this reference direction. And then it's straightforward to show that on the wave functions, you have this Lie derivative with respect to different generators of SL2C, so the Lorentz transformations. And then you have different W derivatives acting on the reference direction. And so given that, you basically have, moving this part to the right-hand side, a statement about the transformation of in the bulk equal to a transformation in the reference direction. And so I promote that to then the operator statement in the 4D Hilbert space. And what you have now is a statement about what you expect for the representations of SL2C in the celestial CFT. So if I were in radial quantization, then I would have the Hermitian conjugation give me L with the negative I, so L plus 1 turns into L minus 1. But given the 4D Hilbert space Lorentz generators and how they're represented, you end up getting a L's going to L bars with the same I. And so that's a problem, quote unquote, in the sense that if I have a primary descendant, normally if I take an inner product then with another primary descendant, I would get 0 because of the fact that this Hermitian conjugation is effectively like acting on the other primary with something that annihilates it, L1. And in celestial CFT, that's not the case. So I can find all these primary descendants, but I'm not guaranteed that they're going to be null. So one other thing to point out in this is like just a shout out to some of Banerjee's early work, and then also the work by Hamada, which is connecting the little group transformations to large gauge transformations. And essentially now the highest weight condition for me, which you can, I guess, have fun with just from the point of view of the wave functions, is really related in the Hilbert space to the fact that you don't have continuous spin representations of the little group. Okay, so in celestial CFT, we're going to see that the wave functions, from the wave functions, that some of these primary descendants are identically 0. So you take derivatives and they land on 0, and this is like the ones that Andy was talking about, and they're trivially null. Now, other primary descendants are going to reduce to contact terms in celestial correlators. And so I would say that within this range of delta that Andy was referring to in his talk, actually the first couple values of those delta is a type where you land on something that isn't quite identically 0, but still if you were solving for something with no contact terms, then you would almost treat it like it's zero. So this is the type of distinction from the point of view of looking at the wave functions, like draws attention to that, which is nice. So the next part of my talk, I'm going to try to just classify the primary descendants of the radiative conformal primaries. And in the last couple slides where I was talking about the tetrad and the spin frame, I now can just write down in a very simple way all of the different bulk spin wave functions for these guys. So basically just tensor products of M and the spin frame guys give me all the radiative modes, and I can continue this for any half integer value of the spin. And this is all a massless case. And the same thing with these shadow modes here. So great. So now I have these guys, and I'm going to basically look at when do they have primary descendants. So the type 1 case. So everything I'm doing right now is radiative. So the parent guy has spin j equal to s. Primary descendants are going to exist basically when you're starting on the principal series as your basis. But part of the work with Laura and Andrea and also Andy is to look at, I guess, like when you go from delta on the principal series and you analytically continue to different special values of delta, that's where you find this interesting physics. So the question would be normally like, do you have to augment your basis? Or is it that somehow you're finding these nice factorizations when delta is taken to that with an amplitude? So it's going to be a very different type of bootstrap eventually if we do have a nice way of formulating it. So when delta takes these basically negative integer values here, which is the shift by the spin, you have type 1a primaries at level n and type 1b primaries level 2s plus n, and those vanish identically. So in the states, most of the states that Andy was talking about with this infinite tower correspond to guys of this type, where now J is either plus or minus the bulk helicity. And you get this these finite dimensional modules where you're descending with the left or right-handed guys. And so at some point they terminate. So the primary descendant for me is literally just equal to 0 as a wave function. And so that's where it's finite dimensional for the ones that fall under type 1. So this is any delta that's less than 1 minus s, that's integer. Now, type 2 are radiative primaries with delta is 1 plus s minus n. And so these guys descend to descendants where all of the value of delta of the, so for any fixed spin, the delta at which you have these type 2 descendants are always going to be 1 plus s. And there's a range of spins basically just before and just after the radiative guys. So we're going to see how these fit into celestial diamonds very soon. So I'm going to not dwell on it for a moment because it's going to be the more interesting part. For type 3, I have primaries at delta equals 1 minus s, and they descend to their shadows. So the unique type 3 is somehow between the two types. And essentially, if you take one of the primaries and you take a certain number of derivatives to land in the primary descendant, you land on the opposite helicity guys, the shadow transform of the one you started with. So from the point of view of wave functions, you can look at it. And so one of them would correspond to the subletting soft theorem, and the other guy would correspond to its symplectic partner, basically. So these guys are the ones that don't have an obvious asymptotic symmetry interpretation, but it's kind of neat that they kind of highlight themselves in the way that they appear with these null state classifications. So celestial diamonds. So the namesake of this talk is basically named after the following structure that we see. We see that we're going to talk about now, we have all of these descendants of radiative primaries. So if you take a value, I'm just going to look at the graviton, say, I look at j equals -2 and j equals +2, and I can find all of its primary descendants. When I have delta less than a certain value, I end up getting 0. So I have these finite dimensional modules that have interesting implications for looking at like the OPE coefficients to all orders. Then I'm going to run into this most subleading soft theorems. And then I'm going to run into the soft theorems with the asymptotic symmetry interpretation. And I found all of their primary descendants. But for the ones where there's this asymptotic symmetry interpretation, I'm going to advocate now that I really want to add another mode back in at basically at the top of the diamond that I was showing from the point of view of the representation theory of SL2C. And that those guys are then going to take into account the shadow and helicity redundancies that have plugged this a bit. And then also correspond to the set of operators that you would add that would capture this spontaneous symmetry breaking dynamics of celestial CFTs. So there's a couple examples where we know what they are, and then you can check that it works. And then there's some where it connects to other interesting literature that's going on. So the claim I'm making now is that for each conformally soft theorem, there's a pair of celestial diamonds corresponding to the Goldstone and memory analogs of it, of the associated asymptotic symmetry. So now I'm going to talk about the gravitational case in detail. So I'm going to have a bunch of figures right now. Okay, so let's spend as much time as we need to unpack this. This is a delta equals 1 Goldstone or memory mode, which corresponds to basically this log of x squared version. So one thing I guess to keep in mind is if you look at the wave functions here, you can see that whenever I have the m's or m bars, that's going to be a radiative primary. And so what's happening for me now is I'm saying that I can take derivatives of it just to construct the descendants where we expect from the representation theory there to be a primary. And you can see that there's this bulk profile that's non-trivial. So the primary descendants are not identically 0, but they are, in some sense, the null states that Banerjee was first imposing is the difference of left and right guys, and that still holds at the level of the wave functions because basically they both descend from a parent guy. So these parents are interesting because if you look at, for instance, the top corner of the memory guy, so on its own, this log of x squared profile isn't quite ideal. Like when you go up, you don't necessarily always obey the same equations of motion. So you can ask, is it really a primary descendant if it would be descending from something that I want to exclude from my phase space because it's not a radiative solution. But what is interesting is that basically if I, depending on the I epsilon prescription I pick for that guy, I will land on either the conformally soft modes when I descend from like that are used in Donné and Strominger and in Poom, or I will land on one or half of it or the other. So for instance, in the recent paper with Nima, Andy, and Monica and Anna, they land on a particular half of the mode proposed with Laura and Andrea. And then me and Andrea picked out the other half because that other half is the one that its parent is the Eichelberg-Sexel geometry. So in some sense, you're kind of seeing that not only we'll see in the next couple of slides that the dressing is relevant to talking about the Goldstone mode dynamics, if you want to look at some effective theory of these conformally soft modes, but it also has this nice interpretation where, like, sure, this could be like the Eichelberg-Sexel geometry, say in my scattering. So that's fun. And the other thing to point out here too is that the fact that these two guys, and anytime you have these celestial diamonds, the left and right corners are related by shadow. And so that's, I guess, capturing the fact that you have the shadow redundancy at delta equals 1. So the two helicities giving the same theme is because they naturally should be thought of as descending from a parent mode. And I think in some senses are appreciated for the leading cases in the papers by Andy and friends looking at the dressings. Okay, good. So let's proceed then to the sub-leading conformally soft graviton. So you can have memory and Goldstone analogs of each of these diamonds. You have a distinction in the sense that now if you have a left to like one helicity versus the other helicity, the shadow doesn't take you to the other helicity. So you no longer have a redundancy in the shadow. So if I look at a given descendancy relation here, what I'm seeing is the fact that the mode that, say, Taylor and others would find by taking the scattering amplitude and analytically continuing the dimension to delta equals 0 before taking the shadow, those two guys are in the same diamond. So if I add a mode here at the top, which is going to be the topic of the last part of the talk, I would basically be capturing both the shadow mode, which would be diff S2, and the super rotation mode. And so the kind of fun thing about it is, from this point of view of just looking at this SL2C representation theories, we're going to see like another motivation for these, like this stuff that like Kevin has worked on, Kevin Neugen, regarding the effective action for reparameterization modes where you break diff S2 down to the super rotations. So what I want to point out here is in the two iterations of the diamond, you have both the stress tensor, which is measuring the soft, like the soft charge, and you have the dual guy, which is basically the pure gauge mode. And so you have these diamonds for both, and you also then have candidate fields at the tops of the diamonds for both. So one thing I want to point out now is, okay, so there's elements of the story that have appeared in, say, the work of Banerjee and others, but by taking this approach, you can easily see how it generalizes to any spin. So on the right-hand side of this slide, I've just pointed out the spin 0, 1/2, 1, 3/2, 2 examples, and you can imagine how it generalizes. So what you're seeing here is that the most subleading theorems do not have an obvious asymptotic symmetry. And so for me, that's this sub-subleading graviton here, which are these X's on these diagrams. For the gravitino, there's should be a subleading Tino theorem, which sometimes isn't as highlighted or compared to the leading gravitino theorem. For EM, it's the classic Lowe's theorem. And then you also see the spin 1/2 asymptotic, like the non-asymptotic symmetry associated but related by supersymmetry soft theorem at delta equals 1/2. So that's kind of nice that I guess by looking at the structure, you kind of can see where all the soft theorems should appear. And you then also see if you went to higher spin fields, where the soft theorems would appear, where the dressings would appear, which I'm claiming are now these top guys here. And where, I guess if you followed Banerjee, somehow the soft charge operators that he's constructing would be at the bottom here. And so if you then take this approach and then reinterpret what Banerjee is doing, the claim would seem to be that in higher D, you still have these set of modes at delta equals -1, and somehow the bottom of this figure gets lower and lower when D goes higher, because it's symmetric around delta equals 1 right now, D equals 1 right now, which is, sorry, delta equals 1 corresponds to the fact that it's D/2. Okay, so good. Okay, so you have this nice structure where you can see basically what's happening in every spin. You can see the different soft theorems appearing as different celestial diamonds. And now basically if I started from the normal, like taking delta goes to 0 or delta goes to 1, I would normally just have the corners here of this diamond. By adding in the dressing, I'll be adding in a couple of states at the top of the submodule. And then if I look at the intersections of these two submodules, I land on what become contact terms. So for when Eddie was talking about this infinite number of guys, the type 1, the primaries with type 1 primary descendants are all like lying above these. And so if you look above them, then you'd actually normally have just zeros when you descend. Here you land on something that's a contact term in correlation functions. And so if you want to still say that's somehow null, it's coming from, I guess it seems like the soft dynamics rather than from the kinematics there. And so if that's the case, then somehow all the shaded region becomes only contact term supported in conformal correlators. And then you still have an infinite number of descendants on either side here. So now I'm going to focus on these top guys and show that at least schematically, you can then extend the last part of the paper with Nima and Andy and friends to these subleading dressings. And this is going to, so I want to put a little bit caveat here because like the things factorizing in gravity is less solid. And so the operator, I guess this operator that I've written down right here in Akuri and Choi is technically already caveated there with the following. So first of all, they're looking at only the leading order and the coupling, and then also these creation operators. There's a statement in that paper about it being only over all polarizations and not just the physical ones. But for our point of view, if we focus on the physical polarizations, we're going to see that they do the dressing in the way that we need it to. And then I'm going to talk about how we expect it to extend to not just 3-level. So if I just look at this expression and I perform the trick that was neatly proposed in the last paper, 2 papers ago by Andy, or maybe 3 by now, that you, instead of for the Faddeev-Coolidge dressing, picking an arbitrary, some sort of profile here, or one with a cutoff in the integral over k, if I let it extend all the way from 0 to infinity, then I can see that there is a definite power of the energy here of this k is the soft, I guess, graviton in this case. And if I do that, then I see that the first term corresponding to the leading soft theorem would pick out a delta equals 1 mode, and then that the subleading term in this proposal picks out a delta equals 2 mode. Now, I take that with what I had mentioned before. So if I am looking at the radiative modes at delta equals 1 and delta equals 2, I said that I know that those guys are descending from something else. So if I take the delta mode as a level 2 descendant and the delta equals 2 mode is level 3 descendant, then that the differential operators that are there are enough to basically localize this smearing here that's appearing. So I can integrate by parts then basically by knowing that these delta become primary descendants. And then I land up on a dressing where basically now I have this C, which is the mode that's in the paper with Nima. And then I have now a candidate dressing corresponding to these reparametrization modes that are related to breaking diff S2 down to super rotations. So I want to put the fact that it's still somewhat schematic because I am trusting expressions, writing expressions in exponential that technically would be probably best treated as still like the first order terms. But if you do formally write it in exponential, then one could show that if you basically add these dressings in, you would remove the TO singular terms in the OPE. So now I want to say that, okay, there's some interesting other results where you see how this would get corrected. So Temple and others back in the day showed that the stress tensor gets a one loop exact correction. And so the fun thing about that is that correction is mixing the spin memory version of this parent guy that you're adding in and the leading soft graviton memory modes. So basically these different soft modes that are all appearing at delta equals -1 for gravity are mixing amongst each other in loop corrections. So then the other thing about pointing out this dressing with the F is that it gives us a chance to have a non-zero central charge. And so if you're looking, this is trying to do the subleading soft graviton analog of what otherwise would be the very interesting computations by Andy and friends using cusp anomalous dimensions for the leading case. Is that, so even if you don't formally, I guess, yet know that you can trust treating this amplitude as being factorized in the gravitational case, perhaps with the conformally soft version of it, because you're trying to demand that the OPs are regular. There's a way to do it in a way that might not be obvious from the point of view of like actual factorization from in this momentum soft limit. So if that's the case, even formally though, at least, you can talk about the correlators between the Fs and the Es. So the Es right now are the memory parents, and those would correspond to looking at multiple soft graviton limits in the typical case. And you would find, I think that the papers of Taylor et al. And others who've looked at the double soft limits would say that that should be 0 central charge, and similar with some of the levels before you add in, say, magnetic monopoles in the I guess old but interesting paper by Angelica and Andy and others. So now with Adam, a couple years ago, and Andy and friends, we motivated that the pairing between the super rotations and the soft charge give you a non-zero off diagonal central charge, say. And so then basically, if you take that structure and add some arbitrary parameter C here, you could imagine that once you make sense of the dressing, you can extract from collinear behaviors of celestial amplitudes what the value of C would be. Not claiming it yet, but I mean, this is the point is, the point for me is that by just looking at these representation theory of these SL2C, you kind of land on seeing that you want to add these dressings in. It addresses the question of whether or not you should have looked at shadow modes or not. You see the shadow redundancies are coming from the fact that there's really this lower spin mode that's appearing there. And then the fun thing about it, this now connects to the story by Neugen et al., where you're basically looking at now these reparameterization modes on the celestial sphere as being this dressing that you need to add. And this connects nicely with both recent work in CFTs, where they're pointing out the fact that the shadow stress tensor and the stress tensor are descending from this guy where you have the same elective, I'm going to pronounce it wrong, action describing that symmetry breaking. And then also, I think it connects nicely with other people who are speaking at this this conference, looking at like co-adjoint orbits of BMS, et cetera. So that's the kind of thing I wanted to leave off on, and to point out that we started from something a priori relatively simple. We're looking at SL2C. Like, you obviously want to look at Poincare too, because like there's so much power in these symmetries that it's fun that you already kind of land on this story where you're seeing how the stories of how you're exploiting null states, examining the roles of shadow versus not shadowing and the basis there, constructing conformally soft dressings, and then also trying to construct an intrinsically 2D effective description of the conformally soft dynamics, kind of tied together from just looking at primary descendants of SL2C. And that's what I wanted to say. And I thank you guys very much for listening.